Okay, well, to pick up where we left off in class last time, we were just about to start talking about the evolution of atomic theory. And we know that from what we were talking about in class, that we had evolved up to the point where scientific community anyway, had finally basically decided that atoms really do exist after about 2,500 years of believing that they didn't, thanks to Aristotle. and But Dalton's theory, while he got a lot of it right, he didn't get everything right. Dalton didn't believe that there were any kind of internal structure to atoms. He thought that they were just sort of featureless little spheres, like billiard balls. He didn't know that there was any electrical charge involved in atoms and that kind of thing. So over the years, as scientists investigated in more and more detail with better and better technology, they were able to find out that while certainly Dalton was right about atoms existing, and he was right about most of what he said, his theory basically needed some elaboration. He didn't say everything that was relevant about atoms. So for one thing, what are atoms themselves made of? Dalton didn't really address that question. Atoms, he said, were as far as you can go. That's the smallest unit of matter. There's nothing smaller, end of story. And are they, and another question would be, within the atom, is there any kind of separation of parts? Is there any kind of internal structure of an atom? And how are those parts, if any, arranged? Okay. So it turned out over time that the situation was more complicated than what Dalton had theorized. Still, he did pretty well for 1807. The electrical properties of atoms began to be discovered later in the 19th century. So Dalton's theories were basically sort of state of the art in terms of atomic theory for probably a good 70 or 80 years before additional information began to come out. Let's see. So scientists began discovering the existence of positive and negative charges within atoms, which meant, of course, that there must be some sort of internal structure in the atom to have some sort of differentiation between positive parts and negative parts. You need an internal structure. It can't just be a featureless billiard ball. Thomson in the 1890s, 1891, developed what became known as the cathode ray tube. The cathode ray tube is essentially the same idea as the picture tubes on older TVs or computer monitors, the really big, heavy ones, where you basically create an electron beam which can shoot through space inside a glass tube that has been evacuated. So it's essentially a vacuum inside the glass tube. That electron beam can shoot through space and hit the end of the glass tube in a certain spot. And you can actually steer that electron beam by applying electric currents to positively and negatively charged plates around the electron beam. And that's how an old TV worked. Basically, you got a single electron beam that's being sort of moved back and forth to different spots on the screen really, really fast. And that's how it creates the picture. Sort of like a laser show where you can sort of draw a picture with a laser by moving the laser beam around really quickly. And if you do it quickly enough, it's too fast for the human brain to register the individual movements, and it just sees it as one sort of continuous picture. Anyway, he applied high voltage across electrodes inside a sealed tube, and he found that the beam, he didn't know yet about electrons. He was just working with these sealed glass tubes, and he found that this beam that he was creating bent away from the negative terminal and toward the positive terminal when he applied voltage to two electrodes, which means that the beam must be made up of negatively charged particles, because like charges repel and opposite charges attract. It's sort of like the north and south poles on a magnet. He also found that magnetic fields could affect the position of the beam also. he calculated anyway, he calculated the mass to charge ratio of the particles in the beam. And he found that in terms of mass anyway, the particles were much, much smaller than atoms. And this is what it was eventually named the electron. He also found an electron was derived from the words electric ion. It's sort of contracted into electron, and that was 1891. You don't need to know the dates or things like that, but anyway, he found that he basically got the same results no matter what element he used for producing these electrons. So an electron from one element was indistinguishable from the electron for any other element. So Dalton was right when he said that the atom is the smallest unit of matter that has the same properties of the overall substance, but he was wrong when he said that there was nothing smaller than an atom. It's just the atoms are made up of protons and neutrons and electrons, as we know now. And what distinguishes the atoms from one element from another is how many protons and neutrons and electrons there are. But there's really no difference between the electrons of any one element and any other element. You could take an electron from hydrogen and an electron from lead, and you wouldn't be able to tell the difference between them. They're exactly the same. Okay, so he found that they're negatively charged and they're present in all elements. And that was the electron. A few years later, a guy named Millikan came along and did what's known as the oil drop experiment. Actually, it was a series of experiments. He found that oil droplets, little tiny, very, very small oil droplets, could be easily gain electric charges and then could then be affected by electric fields, say the charges applied to electrodes or metal plates on either side of the container that the oil droplets were in. And naturally, the oil droplets would, if there's no electric current applied to the plates, the oil droplets would just fall because of gravity. But he found that if he applied an electric current to the plates on either side of the container, he could actually slow the descent of the oil droplets or even reverse it. And that was because the electric charges on the plates were interacting with the electric charges on the oil droplets. Anyway, doing that work, he calculated that all of the charges were multiples of this unit known as the coulomb. And they were all multiples of 1.6 times 10 to the minus 19 coulombs. That's not really a number you need to know. Anyway, he concluded that there must be some basic unit of charge, and each of those units has a charge of 1.6 times 10 to the minus 19 coulombs. And he concluded that that must be the charge on each electron. And what we've done today is we've just taken that 1.6 times 10 to the minus 19, and we've called that 1. That is 1 unit of charge. And so the charge on an electron would be normally referred to as -1 because it's a negative charge and it's equal to this. It's basically 1 multiple of this. And also, once the proton was discovered, it was found that the proton had the same charge, only it was opposite in sign from the electron. So the charge on a proton is called +1, or in other words, positive and 1 multiple of this. Okay, he also was able to combine this information with the mass to charge ratio that Thomson calculated and come up with the mass of an electron, which is, and this is something that you can look up if you ever need it. You don't have to memorize that, but 9.107 times 10 to the minus 31 kilograms. That is a really, 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 really small number. It's even small by the standards of atoms. Okay. The fact is, of course, and this was known even in Millikan's time, that atoms have no charge overall. So he put 2 and 2 together and said, okay, if we've got all these negative charges in an atom, but there's no charge overall, that must mean that somewhere in the atom, there's an equal magnitude of positive charges that will cancel out the negative charges. And he was right. There are positive charges, and their total charge does equal and cancel out the negative charge from the electrons. in trying to figure out how these things are arranged within the atom, there was a series of developments. One of the more interesting models for how they might be arranged was called the plum pudding model. Thomson came up with that. And he basically envisioned it being like the famous or infamous English dessert known as plum pudding, where you've got sort of a mishmash of gelatinous stuff with little raisins spread throughout it. English food, what can I say? Anyway, in this analogy, he was seeing the electrons as being the raisins, and that gelatinous mass, the pudding, he was seeing as being the positive charge. And it was sort of like a mass of sort of undifferentiated positive charge with these little raisins of negative charge stuck in it. And so he didn't think that there were actually particles with positive charges, which we now know to be protons. He didn't believe in that. He thought that it was like one continuous mass of positive with some negative little bits here and there. The Saturn model, which is something that you don't actually hear of very often, but the Saturn model was developed by a guy named Nagoka in Japan, and at about the same time as the plum pudding model. The Saturn model actually was quite a bit closer to the way we now view the atom, but actually for a time anyway, the plum pudding model held sway, at least in the Western world. Nagoka was working in Japan, and communications weren't what they are now. So it's just possible that a lot of people hadn't heard of his ideas. But he basically envisioned it as being like the planet Saturn, where you have a positively charged sphere and sort of a halo of negative charged electrons around it. And again, the positively charged sphere is what we now think of as the nucleus. And in his version wasn't quite right, of course, because he envisioned the sphere at the center of the nucleus as being just basically a solid mass with a positive charge. He didn't see it as being made up of separate particles called protons and neutrons. It was just one solid mass that has a positive charge, and the number of electrons in the halo around it just happened to be enough that they canceled out the charge on the positive nucleus. And that, as I said, is quite a bit closer than the plum pudding model to what we see the atom as today, but it's still not quite right. But they're getting closer. A big development came a few years later when Ernest Rutherford did his what's known as the gold foil experiments. And he basically took alpha particles from the decay of radium and shot them at a thin gold foil. That right there is the lowercase, at least the way it looks, lowercase Greek letter alpha, at least the way it looks when I write it. Sometimes it looks more like that. When it's printed, it looks more like this. And when it's printed like this, you can kind of see how it developed into our current lowercase a. But when it's written by hand, it often looks more like a fish. Anyway, alpha particles are positively charged. And he shot them at this thin gold foil, a very thin gold foil, made up of gold atoms that were only a few atoms thick. And the results were quite surprising. Based on the previous model of the atoms, he expected most of those alpha particles to just bounce back at him because they physically hit something and bounce back. But what he found was that most of them went right through the gold foil. Some of them were deflected a little bit, but most of them went right through. And only a few of them bounced back at him. And what he concluded from this was that there must be a small area of positive charge in the nucleus, or I mean in the atom, and a whole lot of empty space, because that's what allowed the particles to pass right through. It was the positive charges that, the alpha particles that bounce backwards, that's probably just a physical reaction, like a ball hitting a wall. the alpha particles that were deflected passed through but went off at an angle, that would be because they were repulsed by the positive charge in the atom. Okay. And the fact that most of them went right through without even bending led him to conclude that there must be a lot of empty space within atoms. And in fact, most of the volume in an atom is literally nothing, empty space. Okay, and he also concluded that any positive charge present must be concentrated in a very small space within the atom, which has a relatively large mass. And that, of course, is the nucleus. So atoms are basically a small, heavy, positively charged nucleus surrounded by small, light, negatively charged electrons, which are far apart from the nucleus and far apart from each other. So in an atom, a vast majority of the space within an atom is literally empty space between the electrons. And the nucleus is this tiny little thing down at the center. On the other hand, a vast majority of the mass of an atom is in the nucleus, and the electrons themselves weigh practically nothing. And of course, the huge amount of empty space between them weighs absolutely nothing. So a vast majority of the mass of an atom is in the nucleus, but a vast majority of the volume of an atom is outside of it. It is in fact empty. Okay, so and the electrons are so far apart from each other and from the nucleus that if we had, say, a scaled up atom where the nucleus was the size of a basketball and it was located in our normal classroom at Villa, where we usually meet, the closest electrons would probably be somewhere in the Galleria parking lot. That's how far away the electrons are from the nucleus. And then the next nearest electrons would be, I don't know what else is beyond that, would probably be like a mile beyond that. So there is a lot of empty space in the atom. Further, the nucleus is so small and has so much mass in it that the density of a nucleus is actually about the same as the density of a black hole. You know, the kind of situation where a teaspoonful of that material would weigh as much as Mount Everest. That kind of density. But in real life, the kinds of materials that we're used to dealing with, like, you know, paper or plastic, they have very moderate densities because most of the atom is empty space. So you take that hugely dense nucleus and average that density out with all of the empty space within the atom, where the density is essentially zero, and you end up with densities for matter that are, you know, fairly moderate. Okay. The further research led them to conclude that the positive charges are not an inherent characteristic of the one big blob called the nucleus, but the positive charges are actually held by relatively heavy particles in the nucleus that are, you know, separate from each other, but all in the same space, and that's known as the proton. Each proton has a positive charge that cancels out one electron. So it's the same charge as on an electron, only it's positive instead of negative. So if you have the same number of protons and electrons in an atom, there will be no charge overall. But the mass of a proton is much, 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 much greater than the mass of an electron. About 1,800 times greater, in fact. Further research led to the discovery of isotopes. And it was in 1921 that it was discovered that it's possible to have atoms of the same element that have different masses. So atoms of the same element mean same number of protons, because that's how you define an element, and same number of electrons, because if it didn't have the same number of electrons as protons, then it would have a charge. And we're talking atoms here. Atoms, by definition, do not have a charge overall. So there must be some other particle within an atom that has no charge on it. okay? And that was the neutron. We knew from the ways that masses of various atoms of an element can vary, that neutrons must be relatively heavy. They have about the same mass as a proton, but no charge. And in fact, isotopes are defined as atoms of the same element with different masses. Or in other words, that's because they have different numbers of neutrons. So atoms of the same element mean they have the same number of protons, but different masses because they have different numbers of neutrons. Okay, because the identity of an element is defined by the number of protons, which is the atomic number. So if they're the same element, they must have the same number of protons. But if they have different masses, then it must be this other particle known as the neutron. Okay, so our modern model of the atom, going to a new section now, atomic structure and symbolism. Our modern model of the atom is what's known as the Bohr model, which is sometimes also called the solar system model, which we'll get into more detail on in the future. But anyway, the Bohr model essentially has the nucleus, which is protons and neutrons. At the center, where most of the mass is, but only a small portion of the volume. And then around the outside, you have electrons. The electron, this is sometimes called the solar system model because it's kind of similar to the sun being in the center of the solar system with the planets revolving around it. The difference is that, for one thing, you can have more than one electron per orbit, while in the solar system, you normally only have one planet per orbit. And the atom is three-dimensional, whereas the solar system, all the planets are more or less in the same plane. I guess one of them or two of them are tilted a little bit, but the atom is three-dimensional. So you can have electrons that not only go around like that, but you can have them coming out of the page and going back in, and any other angle as well. So from the outside, because these electrons move around really, really fast, from the outside, the atom would kind of look like just sort of a hazy sphere. What you'd be seeing would be the atoms in the outermost orbits zipping around really fast. And they would be zipping around so fast that they would probably block from view anything in the inner part of the atom. So you have a very heavy, very small but relatively heavy nucleus made up of protons and neutrons, each of more or less equal mass. A vast majority of the atom's mass is in the nucleus. The nucleus is surrounded by negatively charged electrons. The charge on an electron being the same in magnitude, but opposite in sign to the charge on a proton. Electrons being very, very light, about 1/1800th of the mass of a proton or neutron. The electrons are very far apart from each other and from the nucleus, and therefore most of the volume of an atom is empty space. So as a kind of a summary, we've got particles, protons, neutrons, and electrons. The location for a proton is in the nucleus. It has a positive charge, a charge that's we usually state as +1, and it has a mass of about 1 atomic mass unit. Atomic mass unit is just a term that's used for simplicity, and it's equal to the mass of 1 proton or 1 neutron because they have about the same mass. So we call that 1 atomic mass unit for the mass of a proton. For a neutron, likewise in the nucleus, and a mass of about 1 atomic mass unit, but no charge at all. And then the electron is outside the nucleus, -1 charge, and its mass is about 1/1800th of an atomic mass unit, which for all practical purposes makes it as good as 0. So for most practical purposes, we don't even count the electrons when it comes to mass. The mass of an atom is normally given by the number of protons and the number of neutrons. And the electrons, even in the largest element out there, it only has enough electrons for about 0.05 of an atomic mass unit total for all of the electrons. as opposed to about 120 atomic mass units for the protons and neutrons. So counting the electrons, that might take you from 120 to 120.05, which is not worth the effort, really. So we don't count the electrons toward the mass. Okay, the diameter of an atom is about 10 to the minus 10 meters. Atoms of different elements, of course, will have different exact sizes, but most of them fall within that range, something times 10 to the minus 10 meters. That's why the unit of the angstrom was developed, because 1 angstrom is 10 to the minus 10 meters. And just for comparison, the diameter of the nucleus is only, of a typical atom, is only about 10 to the minus 15 meters. So in other words, the diameter of a typical atom is about 100 times, or 100,000 rather, times greater than the diameter of the nucleus. So that really tells you, yeah, most of that atom is empty space between the electrons. Most of it's in the nucleus, but it's very small. Empty space, yeah, we already said that. Black hole density, yes, okay. So before we start this next part on units of measure for atoms and subatomic particles, let me just end this first segment of the video, and then we'll start up with the second